Hello there, guys, and welcome to our next class for the fourth unit. Just like you know, this is a class that is part of Pickup School and 10th High School. We are working on the subject Physics 1, and today is week number 30. So let's go over our presentation, and let's start with our end in mind. The students will be able to justify planetary and circular motion through the application of Kepler's law's principles. It may seem a little bit complicated right now, but we're going to go step by step so we can fully understand each one of the concepts that I have prepared for you. And here you have a summary of the activities that you need to complete today. First of all, read and summarize topic 3.07. So it's very important to notice that you need to upload the summary that you did about the topic to Educativa. So once you are done with the summary, make sure you upload it to Educativa. And of course, the summary always needs to include the end in mind, the title, the date, and of course, the summary itself. Number 2, do some additional research on the topic to understand it better. So, of course, you need to watch the video right now, you need to read the topic, and try to research a little bit more about it. In case you have any doubts, you can also let me know during our live session. Number 3, share what you found during the live session. Of course, we are going to discuss a lot more about the application problems and about the several principles that are stated in this presentation during our live session. So make sure to be on time today. And number 4, you need to complete practice 1 to 6 from page number 6. So these extra exercises are going to help you a little bit more to understand all of the formulas, equations, and things that we are applying in today's topic. And I suggest that you focus first in, of course, the summary and the exercises. Then if you have some additional time, you can do the research that I mentioned before. If not, you can just stay with what we discussed because, of course, today's lesson is going to be a little bit longer. And by the way, I guess I'm going to have 2 videos for you today. So make sure to double check in the YouTube list that you have right there in case you have part 1 and part 2. So I'm doing this because I would like to have a little bit more time to explain all of the topic and of course all of the application problems that are stated in this presentation. So make sure to double check for the additional video today. And number 5, after all of this, you need to take the evaluation for topic 3.07 in Academics, okay? That will be about it with the assignments today. So let's start with our topic. And today, we're going to start by talking about Kepler's law of planetary motion. So this law is something extremely interesting to analyze because we can find it absolutely everywhere in the universe. And of course, Kepler will actually exemplify the planetary motion with graphs such as the ones that we have on our left. The first one that we have right at the top is going to give us a better perspective on the parts that we are going to have. And we are going to have a center or a central point that it's going to be right in the middle, let's say, of the circle or the oval orbit that our planets are going to follow. We are going to have 2 focus points, and it's important to remember the name focus points because we are going to be describing them a little bit later on. We'll have a vertex, we have our major axis, we have our minor axis. A major axis is basically the longest side that we are going to find. Of course, when we are going to cross one line from a vertex to vertex, from left to right, and from the longest side, of course, the line has to go through the center of our circular motion. And the minor axis is going to follow another trajectory, or if we would like to compare it to the graphs that we have done before, the minor axis will be our y-axis, let's say. And it's called minor because it is smaller than the major axis. All right, and pretty much those will be the main parts that we are going to find in the planetary motion. And we also have another picture right here. Of course, and this is a more realistic example of what the planetary motion looks like. And something very important to notice is that our sun is going to be located at one of the focus points. So remember, the focus point is not like the central point of the circular motion, but it is actually located aside from the central point, okay? And of course, around the sun, there are many planets that are orbiting, such as our planet Earth, where we are living right now. Okay, so now let's go with a little bit more theory that we have right here. So Johannes Kepler stated 3 laws that describe planetary motion in the 1600s. The description of the motion of planets is still accurate, but the reasoning of the law is no longer accepted. So even though Kepler's law can still be applied nowadays, there are a couple of things that scientists don't agree anymore with. So we're going to start by talking about the first principle, or the first law that he discovered, which is the law of ellipses. It states that planets orbit around the sun in ellipses. The sun will always be located at one of the foci, or foci in singular will be focus points. Okay. And pretty much this is what I was telling you about, that our sun is not in the center of the circular motion, but it is located at one of the focus points. All right, that'll be the first thing. And now let's go with our second law right here. So number 2, law of equal areas. If you draw an imaginary line from the center of the sun, and it goes all the way to the center of our planets, we analyze it at different locations, but taking into consideration the same amount of time, the distance that it will have covered will be the same. So it is better exemplified when I was telling you about the focus points, not right in the center. So what we have studied before, and of course relating it to the universal law of gravitation, the closest two objects are from each other, the higher the gravitational pull that will be produced among them. So in this case, of course, if Earth is farther away from the sun, then it is going to have a lower attraction. But when it gets closer to the sun, then it is going to start orbiting faster due to the higher gravitational pull produced by both objects. And probably you're thinking, hey teacher, but what happens is that our planet doesn't really get that close to the sun. Well, when we actually state mathematically all of the orbiting rotation of the Earth around the sun, we're going to find that probably there are changes that are not very noticeable to our eyes, but there are changes, in fact, there are changes. And of course, going back to the second law, what I was telling you about, if we analyze, let's say, 5 days in the rotation of Earth, no matter at which point we start counting and at what point we end up with the time, let's say, of the 5 days, Earth is going to cover the same amount of space, or is going to cover the same distance, even though it is farther away from the sun, or if it is closer from the celestial body as well. Okay, so let's continue. And I'm sorry, I meant to say this space body. I'm sorry, I don't know why I say celestial body. I'm just confused in some terms right now. I'm sorry about it. But anyways, let's continue with our third law. And this is one very interesting law to analyze as well. So the law of harmonies is the third one. So the radio of the squares of the periods of any two planets is equal to the radio of the cubes, or their average speed, or their average distance from the sun. The result for, of course, elevating the formula that we have right there will always be the same for all planets in the same solar system. So this is quite helpful because it is going to help scientists to determine certain values. So if we take a look at the table that we have right at the top, we are going to find out that we have 2 planets. We have Earth and we have Mars. And of course, both planets have different periods. And when we talk about Earth, its period will be 3.156 times 10 elevated to the 7th power. Seconds, of course. And when we talk about Mars, the period will be 5.93 times 10 elevated to the 7th power seconds. And also we have the average distance that they are the ones that they are located. So we have different distances, but what is interesting is that when we applied both formulas, of course, taking into consideration t as well as r, and we elevated t to the 2nd power and r to the 3rd power, then we are going to get exactly the same result. Okay? And of course, talking about Earth and talking about Mars, we are going to get exactly the same result. So in case a scientist would actually want to determine, let's say, the period of another planet that is not Earth or Mars, let's say that we want to find the period from Jupiter, then they can use this mathematical equation in order to find out about the period or even the average distance that this specific planet is located at. And that is part of the 3rd law. So let's continue, and we have a circular motion right now. And when we talk about circular motion, there are 4 main things that we need to take into consideration. For the first one, we have any object that moves through a loop suffers of a force named centripetal force. It keeps the object moving in a circle. Example, a roller coaster. So probably it comes to your mind right now one of the experiments that we did at first in this year, in which I was rotating a water bottle without the top, of course, at the top. And after rotating it, the water didn't come out of it. So, of course, this happens because of the centripetal force. And, of course, because of the circular constant motion, direction, and, of course, forces, when we talk about speed as well, are going to interact in the mass in the objects in order for this to be possible. And if we have any object that is following this direction or this specific motion, then it is going to suffer centripetal force, such as the planets as well. And of course, what was mentioned here, our roller coaster. Then we have run the simulation from page number 2, found in the uniform circular motion section. So this simulation is extremely interesting, guys, for real. Because you can actually play a little bit around with the forces that you find in the simulation, as well as the different bodies that you have right there. Okay, so for example, you have the sun, then you can actually place Earth. You can actually move a little bit Earth from its original orbit and see what happens. So I encourage you to go to the simulation from page number 2. And have fun playing around with forces and with everything you find in there. And once you are done, you can come back to the video, of course, and we can continue with our video. So welcome back. Now let's continue. And in the simulation, the planets move at a constant speed in an elliptical way. An elliptical way actually means that it's like sort of a circle or sort of an oval. And the vector of the velocity is a tangent. It touches the circle, but does not intersect it to the circle. And then we go to the last one. Gravity keeps planets moving in an elliptical behavior. It's gravity. If gravity is removed, the planet will start moving straight in the direction of the velocity. So here you have a picture of what our planetary motion will look like. And of course, if you had a chance of activating the forces, and of course, taking a look at the vectors that are applied here, you will have a better perspective of the way everything behaves. So, of course, at one of our focus points, we are going to have our sun. And right outside of the orbit of the sun, we are going to find the orbit of our planet Earth. And the blue arrow that you see right over here is the gravity force, or the gravitational pull that both objects are exerting towards each other. And of course, this is what causes the centripetal force. And in this direction is the vector of our velocity. So right here we finish with part number 1 of our video. And make sure to click on the follow-up video, part number 2, so you can continue with the explanation.